Inside a million-square-foot building in South Texas, 18 giant spacecraft were recently visible at once. The surprising part is not their size. It is that they are moving through production together. Starfactory is not only trying to build rockets, it is trying to make rockets flow. Traditional launch vehicles were assembled like cathedrals, one precious structure rising slowly. Starfactory replaces that sequence with a network where many ships and boosters advance at once. The famous target is one completed Starship every day. That is ambition, not current output. But the target explains every strange decision inside the building. A reusable rocket cannot change spaceflight if each new vehicle still takes years to build. Production speed becomes part of the spacecraft, as important as engines, tanks, tiles, or software. And the first bottleneck begins with a thin sheet of stainless steel entering one end of the factory. Most of Starship begins as rolled stainless steel, tough enough for cryogenic tanks. That choice matters because the material is strong, available, and forgiving during rapid fabrication. Machines curve each sheet until flat metal becomes the start of a 9-meter ring. The edges meet, and the factory begins turning surface area into structure. Several rings stack into larger barrels, making the body of the spacecraft piece by piece. Automated welders travel around each seam with repeatable speed. Automation handles the geometry that repeats again and again. Human technicians keep the irregular work that still needs judgment. That division matters because Starship is still changing. A rigid line built for one frozen design could become obsolete almost overnight. So the vehicle separates into major zones: nose, tanks, engines, and connecting structures. Crews can work on thermal protection, while another section receives plumbing. The nose section carries payload interfaces and guidance hardware, but it also faces brutal heating during atmospheric return. Tank sections look simpler, but their welds carry enormous loads. Serratas are cold, propellant, vibration, pressure, and acceleration all punish those seams. Building sections independently solves one delay, but creates a new question. How do enormous cylinders move without one central conveyor belt? Car factories pull one chassis down a line, adding parts in order. Starfactory cannot simply enlarge that idea. Rocket sections are too tall, and the workflow changes too often. The answer is a flexible grid of neighboring work cells. Hardware can travel around congestion instead of stopping behind it. Above the floor, heavy lifting systems become the real transportation network. The ceiling starts acting like a second factory floor. Ground vehicles and transport stands handle the other moves. Delicate cylinders stay supported while technicians reposition them. Because each section follows its own route, one delay does not freeze the whole factory. A delayed payload bay does not have to stop welding or tank assembly. That makes bottlenecks visible. Instead of hiding in a spreadsheet, stalled hardware accumulates on the floor. 18 vehicles in different stages make the strategy visible as inventory. Inventory sounds inefficient, but experimental rockets need options. One vehicle can test a change while later builds absorb the lesson. Parallel production accelerates learning only if the sections eventually converge. Otherwise, the factory only creates a larger traffic jam. Final convergence happens late, after expensive work stays accessible at ground level. That keeps repairs from being buried high inside a stacked rocket. SpaceX's planned Gigabay is designed for vehicles reaching 85 meters tall. That is taller than many complete launch vehicles from earlier eras. The building is planned with 24 cells for integration and refurbishment. Final assembly becomes another parallel process, not one narrow doorway. Cranes rated up to 400 tons will lift sections ordinary equipment cannot handle. Late integration preserves flexibility. If plumbing fails inspection, technicians can repair one section without dismantling the whole vehicle. Every completed barrel still faces dimensional checks. Weld inspection, electrical verification, and leak testing decide whether the factory can trust it. A perfect-looking seam can still fail when cold propellant stretches the steel. Tank structures are pressurized under simulated flight loads. Engines create another supply chain. Fast welding means little if engines cannot arrive at the same rhythm. Tiles, electronics, inspections, and test stands all have to match the cadence. Static fire testing proves plumbing, controls, and selected engines together. That is where manufactured structure becomes hardware trusted near explosive propellant. But even one rocket per day would solve only half the problem. Starship's economic promise depends on vehicles returning and flying again. That means the factory must support production, inspection, repair, and refurbishment together. A returning ship brings uncertainty, heat damage, worn components, and contaminated systems can all demand immediate changes. That explains why Gigabay includes refurbishment, not merely stacking. Reuse turns a rocket factory into a service depot. Each recovered vehicle can feed evidence backward into designs still on the floor. A failed component is not only wreckage, it becomes production information. That information affects tools, inspections, and every later serial number. Starbase compresses the feedback loop geographically. Development, manufacturing, structural testing, static fires, and launch operations sit in one coastal complex. Concentration saves travel and handoffs, but it also concentrates risk. Weather, infrastructure failures, or design pauses can disrupt the whole system. None of this proves daily production today. It reveals a machine sized for a future cadence far beyond current launches. Then comes the next question. Can the sky keep up with the factory? The FAA framework analyzed far fewer annual launches than a daily factory would imply. Environmental approval also does not guarantee every flight license. Regulation, range safety, pads, recovery, and demand must scale too. Starship's payload capability turns each successful flight into a major logistics event. Future versions could multiply that pressure on payload factories and propellant systems. High capacity matters only when launches become frequent. Otherwise, an enormous reusable ship behaves like a cargo terminal with almost no departures. So one rocket per day is less a count than a design requirement. It forces every process to expose its limits. The factory is therefore a second vehicle. It is built from cranes, software, work cells, transporters, test stands, people, and flight data. Its hardest task is not forming steel. The hard task is closing the loop from design to flight and back again. If Starship changes spaceflight, the decisive breakthrough may not look like a launch. It may look like an ordinary shift change inside Starfactory. That is the quiet claim behind the whole building. Cadence can become engineering. And once those vehicles leave this building, another problem begins. They must be caught, inspected, repaired, and flown again before the factory outruns the sky.